Now, we will discuss base theorem. Before that, let us discuss one particular theorem. It is known as total probability theorem or theory of total probability, law of total probability. So, let us discuss that. Total probability theorem or law of total probability. So, what it says? So, already we discussed this kind of theorem before also. Let us here we are repeating again. Let A1, A2, An be a set of pairwise mutually exclusive and exhaustive. Let A1, A2, An be a set of pairwise mutually exclusive exhaustive events, set of pairwise mutually exclusive exhaustive events, or we can say that let A1, A2, An be pairwise mutually exclusive and exhaustive set of events, So, what does it mean? So, pairwise mutually exclusive means ai intersection aj, this is equal to phi if I not equal to j, and mutually exclusive and exhaustive set of events means union of A1 union A2 union An is equal to the sample space S. So, that means suppose this is the sample space, then this is just a partition. So, this is A1, this is A2, this is A3, A4 like this, A5, here 5. So, they are pairwise mutually exclusive, they are disjoint set pairwise, and also if you take the union it will be S. Then for any event you can consider the notation event maybe B. Suppose any event B, probability of B can be represented as summation of I is equal to 1 to n probability B given ai into probability of ai. So, this is the conditional probability of. So, this is same as I is equal to 1 to n probability B intersection ai. So, this is we have already proved actually. So, let us do it again, and this is the just a different expression only. So, now because they are A1, A2, An are pairwise disjoint and exhaustive set of events. So, also A is a event. So, A is a subset of S, B is a event, since B is a event, B is an event, B is a subset of S. Hence, B can be written as B intersection S. Now, S can be represented as, because A1, A2, An are pairwise disjoint as well as exhaustive set of events. So, this union is S. Now, if you use the distributive properties, so then this can be represented as B1 B intersection A1 union B intersection A2 union B intersection An. So, now all this set will be pairwise disjoint, because if you take I not equal to j, then B intersection ai intersection B intersection aj, this is nothing but B intersection ai intersection aj, because ai aj are pairwise disjoint, this will be phi. So, that is why they are disjoint, they are pairwise disjoint. Now, you using theorem 1.5, so this is just a finite version of the axiom 3. probability of B can be represented as probability that actually theorem 1.5 it is used here, B intersection A1 union B intersection A2 union B intersection AN. Because they are pairwise disjoint, here we will use this theorem 1.5 says that we can add probability of B intersection A1 plus probability of B intersection A2 because they are pairwise disjoint plus probability of B intersection AN. So, that is this expression we got it. Now, so that means now this B intersection AN can be represented as B given A1 into probability of A1. So, that can be found. Suppose, so here you can see that probability that B intersection AI suppose. So, what is the conditional probability? By definition this is nothing but probability that B intersection AI by probability of AI, assuming that probability of AI not equal to 0, which implies probability of B intersection AI can be represented as probability of B given AI into probability of AI. So, for I is equal to 1 to n. So, hence that can be represented as this is probability of B given A2 into probability of A2 plus probability of B given AN into probability of AN. So, that can be in short form we can write it summation of I is equal to 1 to n probability of B given AI into probability of AI. So, this is useful, we will discuss whenever it is for the base theorem. Also there are some examples also where total probability for computing this kind of probability. This probability suppose it is given B given AI and probability of AI, then any event B can be represented in this way. Now, we will discuss the base theorem. So, base theorem you may have heard or learned. So, that is if you have learned it, so then it will be very simple to understand, but I am assuming that you do not know this theorem. So, I will discuss very slowly and from the beginning I will discuss each and by giving one examples and some more examples also we will study to understand the base theorem. So, base theorem is very useful from the data set. Sometimes some of the conditional probabilities are known, very straightforward to known, but the other way the like kind of the inverse this is not known. For example, suppose we have a attendance of the students, we have some data, and based on the rainfall, like a day is rainy day or non rainy day, this probability that the student is present during the rainy day, given that the day is a rainy day, this may be known, and also probability that the student will be absent, and given that the day is rainy or not rainy day or sunny day, that probability also can be known. But also that day will be rainy or not rainy, that from the data set also that probability known. Now, suppose we ask the question in the opposite. Suppose a student is absent in the class or present in the class, and then what is the probability that day is rainy. So, the probability that given that the day is rainy, finding the probability that the student is present or absent given that the day is rainy, that probability finding is straightforward from the data set. But from the opposite, like suppose if we ask the question, we know that the student is present or absent in the class, what is the probability that day is a rainy day or not. So, that very much useful. So, that we will discuss again, more examples we will discuss. Here consider a manufacturing firm that receives shipment of parts from two suppliers. So, there are two suppliers. So suppose there are supplier 1 and supplier 2. So, supplier 1 and supplier 2, and the manufacturer company taking some parts from supplier 1 and supplier 2, and that parts actually some parts is here. So, it is from the supplier 1. So, we say that this event it is defined like A1 and A2. So, A1 is that probability that the parts will be from supplier 1, probability that of A1 is the event is that the part will be from supplier 1. So, it is given that this information is given. Consider a manufacturing firm that receives shipment of parts from two suppliers. Let A1 denote the event that a part is received from the supplier 1, A2 is the event that part is received from the supplier 2. Now, we get 65% of our parts from supplier 1, that means probability that if you take a from by a simple approach like classical approach, suppose there are 65% is given, that means it is the probability of that any parts if you take, what is the probability that it is from the supplier 1, the probability of A1 is 65%, 0.65, probability of A1 is 0.65. So, this is 65% and the probability of A2 will be 1 minus of that, this is nothing but probability of A2, this is 0.35, 1 minus 65. So, this is 35% that it is from supplier 2. Now, if you condition on the data that it is from the supplier 1, what is the probability that it is a bad, this part is a bad part, and what is the probability that it is a good part. So, that also we know. So, that means probability that it is a good, the parts is good, it is given that it is from the supplier 1, and probability that it is a part is bad, it is from the supplier 2. So, analyzing the data it can be found. So, this is also given here. So, here it is that quality of the labels, the percent parts good part from this it is from the supplier 1, given that it is from the supplier 1, it is 98%. So, this is it is a good 0.98 and this is 98%. So, good part, and this is from it is a bad part given from the supplier, this is 1 minus of that 0.2. Similarly, here also the out of 35%, this will be bad part given that it is from the supplier 2, it is 95%. So, this is the part is good given that it is from the supplier 2, it is 0.95. Obviously, it will be bad, it is from supplier 2, it is 0.05. So, it is 1 minus of that. So, all these information are very straightforward. Now, suppose it is happened that a bad part broke on our machines, suddenly we found that a part is bad. So, we are through for the day. What is the probability that the part came from the supplier? So, all these probabilities are given to us. Based on that, it is asked given a part is bad. So, that means B is given here, we have to find the probability that it is from the supplier 1, it is asked this probability. So, given a part is bad, what is the probability that the part is from supplier 1. So, that means this is the question, we have to find given B, what is the probability that it is from the supplier 2. Similarly, you can ask that what is the probability that it is from the supplier 2 also. If the part is bad, what is the probability from the supplier 1 and what is the probability from the supplier 2 also you can ask. So, now let us find out this probability that A1 given B. So, this is nothing but probability of A1 intersection by definition by probability of B. So, probability of A1 intersection B, just now we have seen that it can be represented by probability of B given with A1 by into probability of A1, because if you expand this, so later we will find this probability of B given A1. So, this is nothing but probability of A intersection by definition by probability of A1, which implies A1 intersection B. So, probability of A1 intersection B can be represented as probability of B given A1 into probability of A1. So, that is why I written it and by probability of B. Now, how we can find the probability of B here? So, that is the question. So, this will we can compute by the theory of total probability. So, here you can see that A1 union A2, A1 union A2 is nothing but whole sample space S. So, that means A1 is supplier 1, supplier 2, all the parts are coming from either supplier 1 or supplier 2, there is no any other parts. So, that from the other supplier. So, all parts actually belongs to A1 union A2. So, that is equal to S. Also they are disjoint. So, they are pairwise mutually disjoint. Here only 2 events. So, A1 intersection A2 is 5 because one of the any part if you consider it is from the either supplier 1 or from the supplier 2. It cannot be possible that it will be both of the suppliers. So, any parts. So, that is why they are disjoint. Hence, by total probability again we can do it. So, B can be, because B is a subset of S, the bad part it is a subset of S. So, B can be represented as B intersection S, which is nothing but B intersection A1 union A2. So, which is equal to by distributed property it is B intersection A1 union B intersection A2. Hence, because they are disjoint, we have already shown this B intersection A1 intersection B intersection A2, that is nothing but B intersection A1 intersection A2, which is B intersection, this is null set because A1 A2 are null set, this is 5. So, they are pairwise disjoint also. So, hence probability of B will be equal to probability of B intersection A1 in union B intersection A2, and because they are disjoint using axiom 3, probability of B intersection A1 plus probability of B intersection A2, and that can be represented as probability of B given A1 into probability of A1 plus probability of B given A2 into probability of A2. So, this is the total probability, we will replace here, and this is called the Bayes theorem for 2 event. By probability of B will be this. So, probability of B is nothing but probability of B given A1 into probability of A1 plus probability of B given A2 into probability of A2. So, this is the probability of A1 given B. Anyone can ask that what will be the probability that the part is bad, but it is coming from, so what is the probability that it is coming from supplier 2? It can be found similarly A2 intersection B by definition of conditional probability. Probability of A2 given is nothing but probability of A2 intersection B by probability of B, and it can be represented as probability of B given A2 into probability of A2 by probability of B, and probability of B just now you computed. So, this is probability of B given A2, probability of A2 by probability of B given A1 into probability of A1 plus probability of B given A2 into probability of A2. So, note that, so this is 2 and this is 1. So, note that this will, if you take the sum of probability of A1 given B plus probability of A2 given B, this will be 1, because this is nothing but 1 minus of this. So, this value. So, now we will numerically we will compute all this value, it is known to us. So, now probability of B given A1, suppose we are also, let us write down this one equation 1 again, A1 given B, so that it can be visible here. This is nothing but probability of B given A1 into probability of A1 by probability of B given A1 into probability of A1 plus probability of B given A2 into probability of A2. So, now you can see that this will be just sum of these two value will be nothing but 1. Now, we will replace the value here to find this. So, what is probability of B given A1? Probability of B given A1 is here, it is 0.02. So, this is 0.02. What is probability of A1? Probability of A1 also given here, it is 65%. So, 0.65, 0.65. So, then here 0.02 into 0.65 plus B given A2, what is the probability that B given A2? This is 0.05, this is 0.05 into probability of A2, probability of A2 is given here 35%, 0.35. So, then if you compute this numerically, whatever the value it will come. So, you have to use a calculator. So, here all these things it is explained here. So, now you can see that this is the Bayes theorem for 2 events that we have already explained, and this is the computation 0.65 into 0.02, this value it is coming 0.4262. So, this value 0.4262. So, you can go through it again. So, this is whatever we explained here. So, that is also given in the slides, and A2 given B also it is replaced. So, you can try here. So, you replace this value, the numerical value, and this is coming 0.5738. Now, if you add these two values, this should be equal to 1. So, this is known as Bayes theorem for 2 events. Now, we will discuss Bayes theorem for n events. So, this is just extension of n events up to n events. Let A1, A2, An be pairwise mutually exclusive and exhaustive set of events. So, let us see that these are the notation. Actually, here it is given A1, A2, An and for any event. So, this is the notation that is followed, as a set of events. Then for any event B, so this will be in a sigma field. Here we assume that the sample space S and sigma field C. We are following the similar notation for any event B. So, that means it will be a subset of S. For any event B, probability that for suppose if you consider any that suppose ith supplier here, n number supplier, ai that bad part ai given B, it can be represented as probability that B given ai into probability of ai by summation of j is equal to 1 to n probability of B given aj into probability of aj. So, now what is the proof? So, similarly it can be proved for 2 events, it is just a extension up to n events. So, very straightforward, we will just go through it. So, probability that for here for I is equal to 1 to up to n, this is ai is fixed here. For you take a1 given B, a2 given B, you can find the probability just changing the value of I. So, now for fixing I belongs to 1 to n, probability of ai given B can be represented as probability of ai intersection B by probability of B by conditional probability, assuming that probability of B not equal to 0, definition of conditional probability, and this can be represented as probability of B given ai into probability of ai by probability of B. Now, from the theory of total probability, this probability of B can be computed. So, B can be represented as, since B is subset of S, since B is subset of S, B can be represented as B intersection S. So, B intersection, because A1, A2, An are pairwise mutually and exhaustive set of events, in union of ai is S. So, this can be represented as I is equal to 1 to infinitive, sorry not infinitive, n up to n, 1 to n. By distributive property, we can write that they are pairwise disjoint. So, probability B can be represented as. So, I am just writing shortly, because we have already discussed several times probability of union I is equal to 1 to n B intersection ai. Now, because they are pairwise disjoint by axiom 3 or theorem 1.5, this is nothing but summation I is equal to 1 to n probability of B intersection ai. So, that can be represented as probability I is equal to 1 to n probability of B given ai into probability of ai. So, this is the probability of B, we replace here So, then we finally we get this is the base theorem, B given AI into probability of AI. So, I did a mistake because here we take fixing I. So, we cannot use this variable again here. So, this is we will take j is equal to 1 to n, here also we will take j is equal to 1 to n, j is equal to 1 to n, because I is fixed here some value, you can change one of the value, then you will get probability of AI given B. So, this is nothing but summation of j is equal to 1 to n, probability of B given AJ into probability of AJ. So, this is the base theorem, just I proved it, because these things already we have done theory of total probability when we discussed, and then this is we can replace here probability of B, it is just a conditional probability, definition of conditional probability, and we are getting this is also a discussed how it is coming. So, this is the base theorem. So, let us do we have already discussed one example. So, this is the base theorem for n events. So, it is given here, you can go through again, and now let us discuss one example, numerical example. So, there are 100 patients in a hospital with a certain disease. Of these, 10 selected to undergo a drug treatment that increase the percentage cure rate from 50% to 75%. So, here it is actually given that, so whenever someone getting a treatment, so a patient got the treatment, we denote the event is T, and if patient did not get the treatment, then we denote by T complement. So, just we write that T be the event that the patient got the treatment. So, then it is already given that if patient may be cured, so C we denote the event that the patient is cured, and C complement that the patient has the disease or it is patient. So, hospital 10% selected okay. What is the probability that the patient receive a drug treatment if the patient is known to be cured. So, patient is cured, C the patient is, so patient is cured, so C denote for the event that random variable that the sorry it is a event that the patient is cured, and T is the event that the patient got the patient this is 10% selected undergo drug treatment, undergo a drug treatment. So, patient got the received the drug treatment. So, the patient oh, sorry, it is not coming. Patient undergo a drug treatment, and T complement is the patient did not undergo the drug treatment. So, what is the probability that the patient received a drug treatment? So, let us denote. Okay. So, suppose C denote that the patient is cured, and C complement is the complement of that, and T denote that the patient received the drug treatment. So, T complement will be complement that means that patient did not receive the drug treatment, C is the patient is cured. So, now what are the possible probability it is given? So, it is given that there are 100 patients in a hospital with a certain disease, of this 10 are selected to undergo a drug treatment. So, 10% actually got the, so out of 100 probably that what is that the patient received the drug treatment, the probability of T will be 10% of the patient got the drug treatment. So, this is 0.1, and probability of T complement, this is nothing but 1 minus of that 0.9. So, here in this case if we represent it in our base theorem, so A1 will be T and A2 will be T complement, and A1 union A2 will be all patients, this is the all Hampel space, and also any patient either it received the drug treatment or it did not, he did not the patient did not get the receive the drug treatment. So, A1 intersection A2 will be null set. So, that is we found from this problem. So, that Now 10 are selected to undergo drug treatment that increase the percentage of cure rate from 50% to 75%. So that means if the patient receive the drug treatment, then the cure rate is 75%. So it is the conditional probability it is given here. So probability that the patient is cured, given that it got the drug treatment, this is nothing but 75%, 0.75, and probability that the patient is cured, given that it did not receive the drug treatment, it is nothing but 50%. So it is this information. So we have to actually formulate this problem by the events, so that because the theorem, base theorem, it is represented by events. So we have to, but in the problem it is some percentage patients, it is written just by sentences or some explanation it is given, but we have to represent it, we have to transform it in the form of our formula. So that we can use the formula base theorem. So here we have to understand that there are 100 patients, 10 are selected undergo a drug treatment. That means 10% of the patient got the treatment. Probability of T is 10%, 10 by 100, 0.1. So T complement will be 0.9. Now it is given that the drug treatment that increases the percentage of cure rate from 50% to 75%. That means the patient is cured, given that the patient got the drug treatment, it is 50%. Probability that the patient is cured, given that the patient got the drug treatment, earlier the patient is cured, given that the patient did not receive the drug treatment, it is 50%, and then it is increased, that means the patient is cured, given that the patient received the drug treatment, is 75%. So that is represented. So given T complement is 50%, given T is 75%. Now what is the question now? Question is that what is the probability that the patient received a drug treatment? That means T is given here, and if the patient is known to be cured, no, this is given, patient is known to be cured. So C is given here, patient is known to be cured, and what is the probability that patient received a drug treatment? So what is the probability that T, patient received a drug treatment, the patient received the drug treatment, given that it is known that the patient is cured. So this probability it is asked. See that all this given, all this probability, this cannot be found straightforward, we have to use the base theorem only. By base theorem, it is nothing but probability that C given T into probability of T by probability of C given T into probability of T plus probability of C given T bar into probability of T bar. So assume that T is nothing but A1 and T2 is, T bar is nothing but A2 and C is nothing but B in the base theorem, then it is B given A1. So it is nothing but A1 given B. So A1 given B is nothing but B given A1 into probability of A1 by probability of B given A1 into probability of A1 plus probability of B given A2 into probability of A2. So you can see the base theorem for two events what we discussed. So here this is the probability of A1 given B, nothing but probability of A1 into probability of B given A1 by probability of A1 into probability of B given A1 plus probability of A2 into probability of B given A2. So if you relate this variable in this way, then you can use the base theorem here. So then we will just find out. So probability of C given T, it is known 0.75 into probability of T is 0.1 by C given T is 0.75 into 0.1 plus probability of C given T complement is given 0.50 plus into P of T complement. P of T complement is nothing but 0.9. So 0.9. So just you have to calculate, you need a calculator. So actually this value not provided here. So you can compute it using a calculator and you can find out the value. So this will be the final answer. So you can find out the closed, what is the final value, simplified form of this value. So this is one example that how you can use the base theorem. So you can go through more numerical problems. So then you will understand more clearly how to use the base theorem. So this is here only two numerical example we studied. So there are many other numerical examples you can find to use the Bayes theorem, how to solve the Bayes theorem, and then it will be more clear to you. So, that we completed the first part here, this discussion of the definition of probability starting from the sample space, definition of events, sigma field say or sigma algebra. Then we discussed classical approach, axiomatic approach, because before that classical approach, frequency approach, and then what are the drawbacks. Then we discussed axiomatic approach of defining probability, and then we discussed some of the important theorems. We proved those theorems, some numerical example we studied, and then we discussed what are the conditional probability and the applications, and then we discussed independence, what is the difference between independence and mutually exclusive events, and then total probability theorem, and then we finally we discussed the Bayes theorem. So, Bayes theorem we discussed 2 numerical examples. So, I hope you are following and you understood, and then you can solve many more problems using these results.